Hello, this video is going to cover Chapter 9, Sections 9.5 through 9.7, and we're going to look at reactions 10 through 12 and 2 and 3. So as I mentioned in our last video, the reactions in this chapter are not presented in numerical order, but I am still going to use the numbers at the end of the chapter. So we're going to start with some reduction reactions. But before we look at that, I want to look at how we use the word reduction and oxidation in organic chemistry. So we know from Gen Chem that in order for something to be reduced, something else has to be oxidized. But in organic chemistry, we only care what's happening to the carbons. So when we use the word reduction or oxidation, it's referring to what's happening to the carbon. As we go from an alkane to an alkene to an alkyne, we are breaking the carbon-hydrogen bond. So we're losing the hydrogens from that carbon. So it's becoming more oxidized as we go up this list. And as we go from an alkyne to an alkene to an alkane, we're gaining those hydrogens and we are going through reductions. So I just want to make sure we understood how those words are used. So we're going to start with reaction number 11 and 12. So reaction number 11 is the reduction of our alkyne. So we're starting with our alkyne here, and we're reacting it with hydrogen and a catalyst. We're using platinum, and we're going to create an alkyne. So it goes straight from that triple bond all the way down to our single bond. And it does platinum here, but instead of platinum, we could have used palladium or could have used nickel. Both of those would have worked as well. So it's very similar to what we saw in our alkene chapter. Now, because this goes directly down to the alkane, we might want to stop it at the alkene. I think I said that backwards. We go from the alkyne directly to the alkane. We might want to be able to stop it at the alkene. So here's our other option. In reaction number 12, we're going to use a poisoned catalyst, which really just means it's a catalyst that's not great at its job. So meaning it only goes through half of a reaction. And this is going to give us a cis alkene because it's going through a syn addition. So here's our alkyne. We're going to react it with hydrogen. And the most common catalyst to use for this is called Lindlar's. And as a result, we're going to create that cis alkene. Now, Lindlar's catalyst is a few different things, which is why we usually just say Lindlar's catalyst. It's made of quinoline, which is this large structure here, palladium and barium sulfate, and methanol. So we have two different ways now to reduce down our alkynes. One goes to an alkane, but what if we want to make our transalkene? So here's the third reaction in this series then. This is reaction number 10. It's called a dissolving metal reduction. So here's our alkyne. We're going to react it with sodium metal and liquid ammonia, and we will make the trans alkene. So now we can go from an alkyne to a cis alkene to a transalkene or to an alkane. And it's making the transalkene because it is an anti-addition. So we do have the mechanism down here. And the mechanism is a little bit different than what we've looked at. And one thing I specifically want to point out is the type of arrow that's shown here. The arrow that's shown here is called a fishhook arrow. So it's only showing one side, and that's because we're only moving one electron at a time. And then in this next step, we can see that it's a regular arrow because we're moving two electrons at a time. In our next, I believe it's chapter 10, we're going to talk about reactions that only involve one electron at a time, so they are called radical reactions. So this is a little bit of a preview for that. But we're using sodium because it has that one valence electron. So its one electron is going to go onto that alkyne carbon. And then we're splitting one of these pi bonds in half. And so one of those electrons is going to go onto one of the carbons, and the other one goes onto the other. Remember, each bond is made up of two electrons. This is called a radical anion. So here's our radical, here's our anion. This is what allows our double bond to be trans. So because there's going to be electron repulsion, these push away from each other so we get that trans shape. And then the ammonia is going to work as a proton transfer source. So we're going to use our lone pair here to grab onto that nitrogen. And so now our compound is neutral, but still very reactive because of that radical. And because it's a single radical, it wants to join another ion. So we have another another sodium in here. We're going to do that one electron transfer. And then again, we end up with our anion to do our proton transfer. So notice that we need 2 equivalents of sodium and 2 equivalents of NH3 for every 1 alkyne. And we end up with our triple bond there. So let's do a practice one with the few reactions we've learned in this chapter instead, to see if it works a little bit better. And we have our alkyne in the center here, and we're going to react it with sodium and ammonia to figure out our product. We're going to create this product and figure out what reagents we need. And we're going to react it with hydrogen and platinum to get a product. And then here's our starting material. We're going to figure out what we need to create our alkyne there. So let's start with the 3 we just learned. If we react our alkyne, I'm going to do a little bit of labeling on here as well. If we react our alkyne with hydrogen and our platinum catalyst, we know that that triple bond is going to get reduced all the way down to a single bond. So I'm going to double check my carbon count here. 1, 2, 3, 4, 5. So I know that I'm going to go directly from a triple bond all the way down to my alkane single bonds. To go from our alkyne to our cis alkene, we know that we need to add some hydrogen to this. And the catalyst we want to use for this should be our poisoned catalyst. So I'm going to put Lindlar's cat to create that cis alkene. And then when we use our sodium and ammonia, we know that this is going to create a trans alkene. So 1, 2, 3, 4, 5. And my triple bond was between carbons 2 and 3. So my double bond should also be between carbons 2 and 3. And we have drawn it trans. All right, the last one in the first video is the first reaction. We have a vicinal dihalide, and we want to react it with something to get our alkyne. So we need to remove those chlorines, and we're going to use a strong base for this. So we're going to use NaNH2 and NH3. Now I want to point out how similar these two sets of reagents look. The difference between them is this NH2. This is NH2 negative with an Na cation to balance it out. The NH3 is in there as a solvent. We generally use whatever our negative component is in its neutral form as a solvent so that we're not adding anything else reactive in there. Over here, we're not starting with anything charged. So there's a big difference between these two sets of reagents, even though they look very similar. So there's our first set of box problems, as I like to call them, our first set of practice problems. We're going to look at a few more reactions. So we looked at 10, 11, and 12. We're going to move on to reactions 2, 3, and 4. So as I said, the reactions are not in the book in numerical order, but I am still using those numbers and presenting them in the same order that we saw in the textbook. So in reaction number 2 here, we're going to use our alkyne, and we're going to react it with excess HX. So HX would be HCl, HBr, HI. Our excess is often abbreviated as just XS, or you might see it written out as 2 equivalent, so 2EQ. All of those would mean the same thing. And when we react this, both of our halogens will go onto the more substituted carbon, and then our 2 new hydrogens are going to be on that less substituted carbon. So this is a Markovnikov-based reaction. For 3A, in this one, we're only using 1 equivalent of that HX. So it's really just kind of half of that original reaction. So we're adding a hydrogen to one of the carbons and a halogen to the more substituted carbon. So again, it is a Markovnikov-based reaction. Now, if we have a internal alkyne, especially one that's not symmetrical, and we reacted this with HX, let's see, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. I'm going to get a mixture of products. I'm going to get some where my halogen adds to that left carbon, and then some where my halogen is adding to that right carbon, because neither one of these is more substituted than the other. So notice that the 2 examples that we're using are both terminal, because they're only going to give us one product. So it's often, with these types of reactions, we will either use terminal alkynes or symmetrical internal alkynes to limit that mix of products. Now, for both of these reactions, the mechanism isn't known yet. This is one of those things that's still being researched. So there are a couple proposed mechanisms in the textbook. They're not ones you need to know, though, because they are not fully understood yet. And in reaction 3B, so it's very similar to what we saw on the last slide, but it is now the anti-Markovnikov reaction, and it can only be used with HBr. So this is very similar to what we saw in our alkene chapter. So we have our alkyne, we're reacting it with HBr and some type of peroxide. So we saw peroxides in our last chapter. There's a lot of different types, and so often written as ROOR. There we go. That's my peroxide. So we're going to add in to our less substituted carbon and a hydrogen to our more substituted carbon to give us that anti-Markov. And then for our stereochemistry, we're going to get a mix of our 2 stereoisomers, so a mixture of that E and Z shape. And then we're going to do up through reaction 5 in this video. So second to last one, in these last couple though, we're looking at hydration of alkynes. So that means we're going to add an alcohol to our alkyne. And again, we're going to see reactions similar to what we looked at with our alkenes. So with that, we were adding water and acid, and we would create an alcohol. With our alkynes, we're going to need a catalyst. So here's our alkyne. We're going to react it with sulfuric acid, water, and then a mercury-based catalyst, and add Markovnikov for our regiochemistry. So here's our alcohol added to that more substituted position. But notice that it's in brackets. So it's in brackets because that's telling us that this is a transition state. It can't be isolated, and it is not a stable structure. And so what it's called is an enol. The ene is because it's an alkene, and the ol is because it's an alcohol. So alcohol ends in ol, and when we do nomenclature with it, it ends in ol, like ethanol and methanol. So together it becomes an enol. Enols very quickly convert into a carbon-oxygen double bond, a ketone. And so when we start with our alkyne and we react it with this set of reagents, we will create a ketone. It will not stop at the enol. We cannot isolate that enol. So we're going to look at the mechanism for this reaction, and it's quite a large one. And this is the first part, and honestly, the second part that we're going to look at on the next slide is the more important part. But here's how the first part works. We're going to do a nucleophilic attack on that mercury cation, and then our water is going to do a nucleophilic attack on that cation that has been created. Here's why it's going to be Markovnikov, because we're going to have our cation on that more substituted carbon. Because we had a neutral nucleophile, we're going to do a proton transfer to get it back to being neutral. So we kind of have an enol here, but we still have that mercury attached. So the last couple are just to get rid of that mercury. So again, we're going to do a proton transfer using the extra hydrogen on that water. So over here, our water became hydronium, and over here, we're utilizing that. And then we're doing resonance right here. So we have a lone pair adjacent to a carbocation, so that's one of our resonance patterns. And then we are going to have loss of a leaving group. So as that mercury leaves, the electrons get transferred to create a double bond, and then these electrons go up onto that oxygen. So notice that we end up kicking off that mercury as a 2+ cation, which is the same as how it started. So that's how we know it was a catalyst, because it leaves in the same form it started. And we've created our enol. So that's the first half of this mechanism. Here's the second half, which is also the more important half. And I say it's the more important half because this mechanism is going to come up a few more times for us. So here's our enol. We're going to do a proton transfer. We're grabbing onto the hydrogen on our acid, and as a result, we create a carbocation. We're going to move those electrons down as part of our resonance to create a carbon-oxygen double bond, and then we're going to use our water to get rid of that extra hydrogen, and as a result, we get that. This process is called a ketoisomerization. The enol and the ketone are tautomers of each other, so again, this falls into that tautomers are constitutional isomers that can be rapidly ended by just a proton transfer. Really, we're taking the proton or the hydrogen that is right here, and it is now attached to one of our end carbons, so meaning this carbon right here. Around a little bit, but also moving that hydrogen around. This is not resonance. Resonance is only moving around electrons. Because we're actually moving an atom around, it falls into a different category. All right, last reaction before we do our final set of practice problems. So this is also in our hydration section, and this is a hydroboration-oxidation. So we saw BH3 used in our alkene chapter. It was a way to add an alcohol in an anti-Markovnikov way. So again, we're doing an anti-Markovnikov reaction here. We're going to react it with a borane. And so the generic way to write this is to write R2BH. So instead of writing BH3, we're going to put R2BH. Here's a couple different examples. We have diethylamylborane. So the R2 are these alkane structures on the side. And then the other option is 9-BBN, which I always think sounds like a droid. And we have this bicyclic that's attached to our boron here on either side. In the second step, we're using hydrogen peroxide and sodium hydroxide, which is the same as what we saw in our alkene chapter. And so as a result, the oxygen is getting added to that end carbon. And because it's added to that end carbon, we're going to create an aldehyde instead of a ketone. So a ketone has a carbon on either side of that double bond, and an aldehyde has a hydrogen on one of the sides. So we create this aldehyde instead. For both of the reactions we just saw, the ketone one and the aldehyde one, if they are internal, there's not any regio control. So if we have a triple bond that looks like this, our carbonyl could get added to either of these carbons because neither one is going to be preferred in terms of stability. They have the same amount of substituents. So this set of reagents or this set of reagents would give us a mixture of products when using an internal alkyne. So again, just like with some of our other reactions, because it can't be easily controlled, we like to use terminal alkynes or symmetrical alkynes products. So with our alkenes, we used BH3. With our alkynes, we're using a boron that has one hydrogen and two carbons attached to it. It actually makes it less reactive, and we do this so that it doesn't react a second time when it has that pi bond still in place. And then our mechanism here is the same as what we saw with our alkenes, and we've added this alcohol, so we've created our enol. So the process that's down here on the bottom is another tautomerization. What's different between the one we saw on our last slide is that this one is acid catalyzed. This is an acid catalyzed tautomerization, and this is a base catalyzed tautomerization. So start with a proton transfer. We're removing the hydrogen from that oxygen, and now we've created an enolate. So it's an enol that is negatively charged. The first step here is some resonance. So we're moving the electrons down to create that double bond, moving the electrons over to create, and we do one more proton transfer to make our structure neutral. So the idea is the same though. The hydrogen that was attached to our oxygen is now attached to that neighboring carbon. One more general thing I want to point out about these reactions is in this one it's acidized. So notice that everything in this reaction is either neutral or positively charged. So when we're in an acid-base solution, we can't have negative charges. So neutral or positive. And when we're in a basic solution, so in this base catalyzed reaction, it's either neutral or so this is something that is pretty much a general rule for organic chemistry and something that we will throughout this semester and next semester. All right, one more practice problem with our new reactions. So again, I'm using a terminal alkyne because it limits our reactions a little bit. 1, 2, 3, 4, 5. And we are going to add this bromine on that end carbon. We're going to react with X, and we're going to figure out what we need to create an aldehyde, and then what we need is to create a ketone. So I'm going to start up over here. We're going to add this bromine, but notice that it's adding to that end position. So I know that this added anti-Markovnikov because it's on that end position. So that means I need to use ADR and my peroxide. Now if I add excess HCl, I know that this is going to add Markov. So 1, 2, 3, 4, 5. So I'm going to draw in my hydrogens. I know my hydrogen will add to carbon 1, chlorine will add to carbon 2, and it's going to add again. So there's my second hydrogen and my second chlorine. Of course, we don't have to draw those hydrogens, but it just helps to show where everybody went. And then to create our ketone over here, 1, 2, 3, 4, 5, just making sure we have the same number of carbons there, we're going to use acid catalyst. So sulfuric water makes H3O+, so we can kind of abbreviate it and write it that way, and then HgSO4. And then for this one, 1, 2, 3, 4, 5, this is an anti-Markovnikov hydration. So we need to add our oxygen onto that end carbon. So I'm going to use 9 BBN. So this is my R2BH structure. and peroxide and hydroxide. And I often use 9-BBN because it's a lot easier to spell than diamylborane. Alright, that is it for this video. Thank you very much.